We are live now, guys. We can begin. Over to you, Rajiv and Roshan.
Yeah, thank you. Hey Aditya,
Sir,
so
yes, sir. Good evening, sir.
good evening. So what is your questions?
Sir, I have a doubt in quick question,
Okay.
and question number is 144.
I think you'll have to tell me what the questions. Now our numbers are different.
Okay, so question is consider a network with n is equal to 11 and m is equal to 54. So the number of triangular subgraph in the given
Oh,
network is
I think this is Karthik's, Dr. Karthik's course, right?
yes, I think.
Yeah, Aditya.
Yeah. Go on, Deepesh.
Yes.
Yeah, I was just saying that I think it's better to share the screen, Rajiv and Roshan, uh, one of you, and then we just go through the questions one by one and see if they have any doubts. Don't you think that would be a better way? So, because like you said, the question numbers are different. So one of us will have to share the screen.
So
Yeah,
I am sharing my screen.
the
Okay.
problem is he's like that's Dr. Karthik's course material.
Yeah, sure, sure. That we will. I will just let them know about that.
Okay.
Aditya, you're sharing your screen.
Yes.
So this is for Aditya, you and whoever will be listening to this recording. That today we will be covering quiz two questions from Nirav sir's part. That means genome assembly, sequence alignment, and so on. Okay. And the Karthik sir's part, we will have a separate live session tomorrow. Is that
Okay, sir.
okay,
No
Aditya?
problem.
So
Okay.
kindly bring up questions related to Nirav sir's part. Okay, and also assignment 11.
Okay, so I have another question that I have doubt in 152. Yes, sir. Oh, sir, this is the question. For two identical sequence of length n, which of the following is true, sir? I think question option number four should also be correct because there can be gap in the best alignment because in the one of the lecture you have also told me that when we
But
are
we are
discussing.
saying it's sorry. Uh, so we're saying they're identical sequences, no? So basically, it'll be one-on-one mapping of each sequence. So there's no gap in that sequence. The two sequences are identical,
Okay, so
meaning
if
meaning
it
that
will be if, if it
sorry.
is not identical, then there can
Then
be
it's
gap.
certainly possible that there are gaps in the alignment. But since the two sequences are identical, there's no gaps.
Okay, okay, and another one is uh, 155. Sir. This
Yeah.
question, average degree, sir.
Yeah. So can you stop sharing? I'll share my screen. I'll show you the overlap graph. So I before that you were mentioning a calculation, no?
Yes, sir, in the group.
Yeah, I think the calculation has some mistakes in that. Oh, this is can you see my screen?
Yes, sir.
So for the given sequence, this will be the overlap graph. So there will be 5 nodes, and totally there will be around 12 edges. Sorry, not 12 edges. So the degree of so this will be two, this will be three, three, and this will be two. So on average, it will be 2.4.
Sir, sir, how there will be two edges? Because in the lecture we were taught that we
You
will
can count,
connect
no?
if a
The
suffix is equal to prefix, and
yeah. So what does this mean? So at suffix t is matches with tg's prefix t. So there's an edge there. GA's
Yes, sir.
suffix A matches with AT's suffix A, sorry, AT's prefix A. So there's an edge. So there are two edges for this particular node. And similarly, you have to calculate for each of these nodes, and then on the average degree will be the final answer. That will be 2.4.
Oh, sir, but there will be age between sir AT and TG, and TG and GA,
Yeah,
and third one will be GA and AC,
yeah,
and fourth one will be AC and CT,
yeah.
and I think that's
T and
all.
TG, CT and TG will also be there, no? Because you have to compare prefix and suffix. It doesn't matter what your initial sequences are.
Okay.
So as long as the prefix and suffix matches, then you'll have an edge between them.
Okay, so we can connect as many as possible.
Yes.
And
I'll stop my.
another okay, sir.
No, please share.
And another question is 163. So this is another question. We have to count housekeeping interaction and disease interaction.
This is again Dr. Karthik's thing. So you can ask this tomorrow.
Okay, so that's all from that's the all doubt I have to ask from quiz.
There was
Now,
sorry. One second before that. In the group there was an alignment question. No, can you go to that question?
Yes,
sequence.
Rajiv, it would be best if you explain that question while in the live session. So there were a couple of questions from
Yeah.
Abhinandan, I think. So you can kindly explain that. Okay.
More of a sequence alignment question.
Yes, this is the question.
Yeah. Deepesh.
Yes.
So the question is correct, but the problem is the options are wrong actually. So it should be +8 in the D option. So I think we can award marks to everyone who has attempted.
Who has attempted? Yeah, sure. So the correct option should be D, which
There's no
is
correct option
+8.
in here. That's
D,
the issue.
thank you. I see. So those whoever have attempted that, then we will, then I think as per the guidelines, they will be awarded marks. Whoever has attempted this question. Okay.
Yes.
Okay.
Any other questions, Aditya?
Sir, in this question, we have to calculate modularity. So, I just due to this, I just think it as a symmetric. Both are
Again,
symmetric, and
can
then
you please ask this tomorrow because this card
okay,
Dr.
sir.
Karthik so far.
Okay, sir. Sir, I have a doubt in sir week 11, sir.
Okay. Yeah. Roshan will answer them.
Sir, I not actually doubt, sir. I have, sir. Uh, sir, I have problem with the whole concept. I'm not able to understand, sir. This,
Okay, so can you mean what concepts are not clear to you?
sir, there's a lots of equation,
Yeah,
and there's two type of graph filter: spectral based filter and spatial based filter.
spatial based
And
physicals. Yeah.
we have three lecture in a spectral based filter,
Yeah.
and in all three there's lots of equation and complex things. So it is hard
Yeah.
to get a
Okay.
deep understanding in all these things. So can you say just go over slightly?
Uh, so, I mean, if you have some any specific questions, like, should I just give a brief overview on what are
Yes,
these
sir.
things,
Just
or
yeah, just brief overview.
okay,
Just share your screen and just a brief overview over the topic, whole topic, and I will able to understand. And if
okay.
I will have doubt, then I will ask it or I will ask tomorrow. Just go.
Let me just. Yeah. I think currently I'm using my mobile phone. I think I won't be able to share my screen, but yeah, let me just try. So, can you mention any specific topics where you have doubts, or I mean, just you just need an explanation for the whole concept, or
Yeah, so just go briefly.
okay, just okay. I'll just briefly go through some
Yeah, because
slides.
it is totally a new thing.
Mm,
And so do I have to so remember all the equation and
Hmm?
everything? Do I have to remember all the equation, expression, everything?
Uh, Equations as such, you don't need to remember everything.
But it's only equation in the
Hmm?
lecture, in the filter
Yeah,
lecture.
that is just for your intuition. Okay, how it comes into place. That is what it's for. But there are some fundamental equations that you have to remember. Let's say for GCN filter, there'll
Okay,
be a
sir.
key.
Please, sir, while briefly, so please mention what should we
Okay, okay,
focus on.
okay, okay. Yeah, yeah. First thing is deep learning over graphs. I mean, I'm not able to share my screen, but I'll just go through.
So can I share my
Okay.
screen?
Yeah, yeah. You can share it and ask any doubts you have in the slides.
Okay. Okay, so here from where it is
This
has started.
okay. So you know what an adjacency matrix is, right?
Yes, sir.
And neural network, what will you pass it as input? Typically, what will be your input?
Mm, yes, sir.
It'll
We will
just be a
pass.
single vector, right? Single vector.
Yes, sir.
And this is a matrix. Adjacency, it's
Yes.
a matrix. So what will you
Yes, sir.
do here to make it into a vector?
Okay, so we have to do some type of conversion to make it, to
Yeah.
convert it in a vector.
Yeah, that is what is flattening is for.
Yes.
Okay.
Okay.
So first row, then the second row, keep on adding until you form a single vector,
Okay. We have to
right?
add every row. Yes.
So the vector will be 0, 1, 0, 1, 0, 0. Okay. And then 1, 0, 1, 1, 0, 0. So it'll just be a single vector.
Okay, sir.
Okay. Converting the matrix into a vector. That is what is flattening. Okay.
Okay, sir.
And that you can pass it to a neural network and then get the prediction. Anything. Okay.
Okay, so for conversion, we have to add every row.
Yeah, that's it.
Means for first row, it will be two.
No, 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 not adding. It's adding is different, concatenating is different. So what you have? One, two, three.
No,
So you
no.
have six nodes, right? Total, there will be 36 elements in the vector.
Okay.
So first row, first six elements, second row, next six elements. So in total,
Okay.
36 elements will be there.
Okay. Okay, sir.
Okay. This you understood? How
Uh,
to
but oh, but what will be shape, sir?
shape will be 36 cross one. That's all. 36 cross one. So see in the see in dimension is given. Coordinately, I mean V dot V, right? Cardinality of V dot V. That means 6 into 6, 36 cross 1. That's your
Okay.
dimensionality.
Okay, sir. I understand.
Hmm.
Okay, sir. And here
So
we
same
have.
thing. What happens here? Uh, let's say uh, there is. Can you go to the above slide? So this one, if you order it by UVWXYZ, you get one kind of adjacency matrix. You can again reorder it, right?
Okay, sir.
According to your
Yes, sir.
wish. It can be
Yes.
ZYXW VU or something.
Yes, sir.
So accordingly, the flattened adjacency matrix keeps changing, right?
Yes, sir.
If that keeps changing, will you get the same prediction again and again if you pass it to a neural network?
I don't.
Hmm? If the
No,
order
sir.
changes, your
Input
A
will
flat
be
in,
different.
yeah,
Input
the
will be
input will
different.
be different.
Yes, sir.
So, so according to the ordering, the input changes, accordingly the output changes.
Yes, sir.
But do you want that actually? Do you actually want that to happen?
No, sir. Because this is the same graph, so we don't
Yeah,
want to.
we don't want that to happen. So that's why we need to develop methods that are both permutation invariant and equivariant. Permutation invariant means whatever reordering you do, the output will be the same. See, there is no
Okay.
P matrix in your output.
Yes, sir. And what is a P matrix?
P is something called a permutation matrix. Like you can swap rows or columns. If you multiply the matrix, P matrix with some other matrix, what happens is you can change the rows, you can change the columns. That is what a permutation matrix is.
Okay, so just a different combination of same matrix.
Yeah, different
Arrangement,
com.
different
Yeah,
arrangement.
different arrangement of the
Arrangement.
same matrix. If you multiply a P matrix with A matrix, it will change the rows, columns. It will just swap it. That's all. You can think of it
And
like that.
so I have one question. So why we are doing this? Why we pass the graph from neural network? What we want?
Ultimately, what we want is a representation of the graph, right?
And what is means by representation?
Have you gone through the previous lectures?
Yes, sir. Yes, sir.
Have you gone through the tutorial also?
Mm, yes, sir. I think yes.
Ultimately, so given a graph, I want an output. How do you represent a graph? You can't give the picture of the graph as input to a computer, right? You need some
Yes.
numbers. You need some numbers to work with.
Okay.
How do you generate those numbers? That depends on the type of representation. Matrix is one. You can represent it as a vector. That again depends on your choice.
Okay, sir.
Okay.
Okay, sir. And so, what is permutation equivalent?
So if you change the ordering in the input, accordingly the output ordering will also be changed.
Okay,
Invariant
so
means it does not have any effect. Equivariant means when you change the input one way, output also will be change the same way. That's it.
but we would don't want to change. So why we will use equivalent variant?
No. It's not like we don't want to change. Whatever happens to input, same thing will also happen in the output. That's what we want.
Okay. Okay.
Output
Okay.
does not change. The ordering only changes.
Okay.
Okay.
Okay, sir.
But neural networks, this adjacency matrix, they are both they are not permutation invariant or equivalent. That's why we need to move over to graph neural networks. Okay.
Okay. So this is the equation.
Yeah. So what do you get out of it?
So we are passing input feature matrix with
And adjacency
adjacency
matrix.
matrix, and passing it from the graph filter, and we are
Hmm.
getting learned feature matrix.
Yeah.
Sir, what is a feature matrix? here.
Feature matrix. Have you gone through what are node features, what are edge features in the lecture? Node features, you will have some slides, right?
Yes, sir.
So each node will have a feature, right? Let's say for a molecule, it can be the type of atom, the type of bond.
Yes, sir.
So that is a feature for a node.
Okay.
But according to graph neural networks, what we want is a representation for an entire graph. So we have a feature for each node, but that feature, what happens is it doesn't take into account the neighborhood information.
Okay.
So another atom can influence this atom, right?
Yes.
So how do we learn it? That's what is the basis of graph filtering.
Okay. So are we passing it through the neural network?
Hmm?
What is the graph filter here?
So
H.
graph filter, it takes in adjacency matrix and feature matrix, okay?
So this is some type of function.
H is some function, okay?
Okay.
That takes in adjacency matrix and feature matrix as input
Okay.
and gives a learned feature matrix. What is there in the learned feature matrix is it has adjacency matrix information. What does adjacency matrix specify? The structure of the graph.
And what we will do with this learned feature after?
Learned feature matrix, you can pass it again to a neural network and then get some predictions.
Okay. So okay. Okay. So
You see how the dimension of features changes after filtering, but nothing happens to the graph as such. Only the features get changed, right?
why it reduce?
That is our design choice. You can either make it reduce, increase, or stay the same. It's according to you. That is again a hyperparameter that you have to decide.
Okay.
Okay, you understand me? What is a hyperparameter and everything, right?
Yes, sir. Yes, sir. From
Okay,
machine learning tutorial, I understand.
yeah, same thing. You can increase, decrease, or stay, make it same.
Okay. And here is a pooling.
Yeah, pooling.
So here,
Ultimately, what we want is a single graph should have a single representation, right?
yes, sir.
So, a graph, it's highly irregular. What do I mean by irregular? Different molecules have different graphs, right?
Different. Yes, sir.
In CNN, how do you do pooling?
Uh, so in CNN,
You
sir,
have
we
learned.
take. Yes, sir.
Yeah.
We take s- some small some matrix and then uh, go.
Yeah.
If
Their
suppose we take
image
the
size
small,
is fixed, right? Image size is fixed,
yes,
right?
sir. Yeah, we take a small size and then
Yeah.
go through the
But can you
every.
say the same for graphs? Different graphs are different sizes, right?
Yes.
So pooling, what happens is you take in the adjacency matrix, you also take in the feature matrix, and you reduce the graph. If you go through the next slide, you can actually see what happens in pooling.
So graph is got reduced.
Reduced. Ultimately, we want one node, one feature. Ultimately, at the end.
Okay.
So this is what
One
pooling does.
one node, one feature.
Yeah, ultimately for graph task.
So uh, okay, so but here we have so two feature, no? From four from box for each node we
See,
have.
one feature means I don't mean the dimension of the D out, okay? Number of feature, I mean, one node, one feature, not the elements in the feature vector. One node, one feature vector, okay?
One node, one feature vector. So, but here also we have one node and one feature vector. No?
No, no,
For
no.
each
That is
we have
for each node we have a feature vector, right?
is for each node. Yeah.
But ultimately we want for one graph, one feature vector. How do you do that? You basically summarize information from all the nodes, right?
Okay.
How do
So,
you
but
that
why?
summarizing information? Yeah,
But
tell
why
me.
we get here only three? We can get two.
That is again your design choice, your hyperparameter. You can get 2, 3, anything.
Here we are passing input feature.
To filter, then I apply activation, again filter, activation, same thing. Same thing like a neural network. You can think it of as a neural
Yeah,
network. That's it.
neural.
Yeah,
Okay, so, and
same thing.
here,
Same filter, adjacency matrix feature.
uh, but here in the above equation, we have just adjacency matrix and input feature matrix.
Same
What?
thing is also there, but extra activation might be there.
Yeah, activation.
Yeah.
So we are multiplying a feature matrix to the activation function.
Yeah. There are different kinds of task. One is node task, one is graph task. Graph task, you'll have pooling with filters. In node task, you'll only have filters. Okay. Think of it like that.
Okay, this is graph. So in graph we have to do pooling because
Yeah, we have to do pooling.
okay because we want same size of graph to pass.
Yeah. Yeah.
Okay. Okay, here sir, this is uh, graph filters.
Yeah.
We have two types of filters: spectral based and spatial based.
Spatial based. So spectral based, what you'll have is mm, think of features as a signal. Okay.
Signal. Okay.
Signal. Okay. Uh, let's say whenever you measure something, there is noise in the signal, right?
Yes.
Let's say you take ECG or something. It's not always smooth, right? There are a lot of peaks, some random noise and everything, right?
Yes. In voice signal also there is some type of
Yeah,
noise.
same thing. There is some unnecessary interference, right?
Yes.
What happens if that is present in our data? Ultimately, we won't be able to learn anything good, right?
Yes. Sir.
So what we want to do here is only extract important information from the feature.
And how it will be decided that what is important and what is not.
So that is why if you go down, there are traditional filters and there are parameter-based filters. See, in the traditional filter, you won't learn anything. But let's say in GCN or Chebyshev filter or something else, what happens is you learn what are the important features, okay, and discard what are not important.
Okay, sir.
Okay, and the learning how it happens, you have a loss function. You have a supervised loss function. You understand by what I mean by
Yes, yes,
supervised,
yes,
huh?
yes,
And
yes.
based on the loss, you update the parameters. That's it. That's
Okay,
what
yes.
happens.
Just back propagation.
Back propagation. That's it. And based on the back propagation, you update the parameters, and the parameters determine which feature is important, which is not. That's it. That is the whole basic concept here.
So okay, this is just like machine learning, no?
Yeah, yeah.
Okay, so and here it is a Fourier GFT graph Fourier transform. So what is
Hmm.
it? This is happening. What is happening, sir?
So Fourier transform is we converted from graph domain to something called spectral domain. Okay.
And what is a graph domain spectral domain?
Graph domain means, can you go slide above? See the first image, that is a graph domain. Okay,
Okay, sir.
this is the graph domain. You have a node, you have an edge, and each node is associated with a feature. That is the graph domain.
Yes, sir.
And the second picture, that is the spectral domain.
This graph.
Yeah. See how noisy it is?
Yes, sir.
We want a smooth curve. That is our objective.
Okay.
So a spectral domain, you can think of it as the signal processing domain as such.
Okay, sir.
But I think you have to read a bit about what Fourier transform is, what it does, why do we do it, and everything. Okay.
Okay. I will just write it down.
I think if you have taken a machine learning course, you might have already been aware of what is the Fourier transform and everything.
No, sir. In machine
Okay,
learning
okay,
and in deep learning also there was no Fourier transform.
okay, okay, okay.
Fourier
I
transform and
think
another one is.
that's it. Fourier transform. Just learn
Just
about Fourier transform. Yeah.
okay. Okay, so here we are changing a graph domain to a spectral domain.
Yeah.
And what is happening below?
So what do I ultimately want to do? I want to filter the signal, right? Remove unnecessary components, keep necessary components.
Yes, sir.
So that is why what this gamma is filter, element-wise function.
Okay.
Okay, that is what it does. I think if you go through the tutorial, you'll get a much better insight on what it is, what
Okay,
it does, and
okay,
everything.
sir. Okay, so I will learn about the Fourier transform and then I will ask tomorrow if I have doubt.
Yeah, yeah, sure, no problem.
Okay, sir. The smooth signal, sir. What is it doing? It is smoothing the signal.
Yeah. So higher the value of C, the smoother the signal will be.
Okay.
See,
And
you have also have the Jupyter notebook for the tutorial, right?
yes, sir.
So try modifying the values of C. Keep on increasing it. Start from a very low value. Start increasing the C value and see how the signal changes, right?
Okay, okay, sir.
You
I
can
will.
do that, right?
Okay, sir. I will do that. So, wait. Okay, sir. And here it is a polynomial filter operation.
Hmm. There, what you have to do is to learn the parameter theta again through back propagation. That's it. Don't worry about it much.
Okay.
See, in the traditional filter case, in the low pass filter, what you don't know, like for each data set, there might be a different value for C. Okay.
Okay.
You don't know how to learn that C. But here you have a value theta.
Okay, just like we have a weight, weight.
Wait, yeah, yeah,
Yeah.
same concept.
Okay, so
You don't need to remember all the formulas, okay?
okay, so.
Just understand the intuition behind it.
So can you explain shortly the Laplacian and sparse matrix?
Laplacian matrix, you know, right? It's degree matrix minus adjacency matrix.
Oh, yes, sir, yes, sir.
And if you take the power of the Laplacian matrix, it is sparse. What do I mean by sparse matrices? Most of the elements will be zero. Okay,
Okay, sir.
that's it. That is what I mean by sparse. So you can try take a Laplacian matrix, any Laplacian matrix from a graph. You might have one from the assignment or something.
Okay, sir.
Try to the power 2 to the power 3 and see how many zeros are there. That's it. Just check.
Okay, sir.
So if you just go through these slides, you won't understand anything. You have to accompany it with some coding or some. You have to do some homework. Okay.
Okay, okay, sir. Mm. Also here, what is a L? L is a
L
matrix.
is the Laplacian matrix. F is the feature vector.
And here we have problem with poly filters.
Problem, just don't worry. It just see there is noise in the learning process that makes it unstable. That's it. Okay.
Okay, sir.
You understand by what is a basis? You have some linear algebra basics, right?
Yes, yes.
So what is the basis? What do you mean? What do I mean by orthogonal,
Yes, I understand this.
linear independence? Same
Yes,
thing.
sir.
Same thing.
So here we have Chevy filter.
Chebyshev polynomial, right? Yeah.
Yes.
You have to remember this expansion. Okay, that's one of the most important thing.
So this one.
Yeah. These are not all basic equations that you have to remember. Uh, this one, the equation for graph attention, GCN. You don't need to remember all the derivation steps, but at least try to remember these the final results or the initial things. Okay, that's it.
Okay, sir. So here there is a lots of no, sir,
Hmm?
equation. So here there is lots of expression.
Yeah. So
So what to
I
do
think
with
you
it?
have to go through step by step. Take an example. Okay. And I think in the tutorial notebook, there is actually a coding example. How to do it by hand from scratch. Okay. Chevy
Okay.
filter. Go through the
Chevy
notebook,
filter.
execute it line by line, and see what changes in each line. That's it. Okay.
Okay, sir. Uh, you were
What
talking
happens
about.
here is the Fourier transform itself. That's it.
So you were talking about this equation that we should have to keep in
Hmm,
mind. GCN
hmm,
filter.
hmm.
Okay.
Yeah. So
What is happening here? Can you explain briefly?
okay, what is happening? So Chebyshev polynomials. You understand what I mean by order, right? Order of the polynomial. K. K
Okay.
is
Yes,
one.
sir.
What happens in K is one? What happens in K is one? This is the first line, right? That is your equation when K is one.
Okay.
Okay.
So
K is one.
we will have
The
y.
yeah,
We
Y.
will get y.
So here your Y will be your eigenvalues of the Laplacian matrix.
Okay.
So go down. So that is how you get your first line. Okay.
First line means this is
Yeah.
first line.
Okay.
Okay.
So and then you simplify it. Keep simplifying it. That's it. T0 will be your identity matrix. That is one, right?
Yes, sir.
And T1 of that one will be your Y. What is Y? The lambda there, right? That is what is written in the second step.
So okay. Yes.
Yeah, right.
Yes. Yes. Yes.
And this is the rescaled one. Again,
Okay.
it will be here. See, one more assumption is lambda max is 2, right? One more assumption. What happens is lambda max is 2. That lambda with the hat becomes lambda minus I, right? If lambda max is 2.
So lambda is a filter.
Yeah,
Uh,
that is a filter. Gamma is the
okay.
filter.
Gamma.
Gamma is the filter.
It's a gamma is a filter. So what is lambda here?
Eigenvalues of like a Laplacian matrix.
Okay, I can find out.
And then You have the filter, right? With the filter, what you'll do Fourier transform, right?
Okay, sir.
Do the Fourier transform, and you'll get the final output.
Okay, with this filter.
Hmm? Yeah.
With this GCN filter, no?
Yeah.
Okay. Uh, this is the input we have to pass.
Yeah. So eigenvalues of Laplacian matrix, you have to pass in as input. That's it for the filter.
And uh, uh, eigenvalue of the Laplacian
Laplacian
matrix
matrix.
we will get but when we have t equal to 1, k equal to 1.
Hmm.
Okay, flying. And
So
so
with the
here,
filter, you do Fourier transform. Fourier transform formula is this one. Instead of gamma, you substitute the value above.
okay,
You get this one. And there are some properties here. You don't need to worry about how this comes into place, but just look into it. UI U transpose is I.
okay.
Can you tell me what the intuition behind this is? Why is it like
U.
that?
Uh,
W-
this is something SVD.
Because U is an orthogonal matrix, right?
Okay, okay.
So this is the intuition behind how it happens. So and then further simplifications, you come to the final equation.
So this is the final equation,
Yeah. No. Come down, come down. There are more simplifications.
and here it is D.
Hmm.
So this is lots of equation. No?
Yeah. You
So,
don't need to remember. Just remember what happens in each step. You don't need to remember the equations. Okay.
okay, so here we assign L is equal to this thing
Yeah.
to the equation.
Yeah.
And but what is D here?
D is degree matrix. A is adjacency matrix.
Okay. So do you remember all these things?
Hmm?
Do you remember all these things?
I. You mean you are asking me if I remember all these equations.
Yes, sir. Do you have all these things in your mind?
See, I can remember most of them because I use it almost every day. So if you
Okay.
keep learning, it comes to you. Don't need to
Yeah,
worry
yeah.
about it.
If you will do it for many months or many years, then it
Yeah,
will
yeah,
automatically.
yeah, yeah,
So how you are doing this? Are you doing anything, sir? Project or something like that?
yeah. It's like that. Yeah.
Okay.
And if you keep reading the book, you will get it.
So
So the reference for
this is
these slides is Deep Learning on Graphs. Okay, a book
okay.
called Deep Learning on Graphs.
And who is the sir writer?
Um, I'm not sure about the writer, but the author is from MIT. Okay,
MIT. Okay. So this is okay. So
this is
I
the
think
reference for
Rajiv,
that.
Roshan, I think
Yeah.
one relevant question here is what is it that they must, given these graph neural network, what is the objective? So definitely they don't need to remember these equations. So
Yeah.
what is it that is expected from students who are taking this course? I think if you could spell that out, maybe it will be helpful.
So you just have to understand the intuition behind how each graph neural network works. Okay. What is your objective? How do we learn those representations? The how do we learn those representations has all these equations. Okay. And each equation has an intuition behind it. I mean, if we keep saying like what happens in this step, why do we do this step? the lectures will be going on for very long. Okay, this is like a compressed version of it. But there are reference books where you can go where they give you the detailed intuition of why they do this. Okay, is that fine, Dipesh? Or
Yes, Roshan. Thanks for that.
yeah, yeah,
So this is the final equation. F dash is
yeah.
equal to theta.
So if you tell me uh, if you ask me what a GCN filter is, I'll just give you this equation. That's it in simple
Okay.
terms. Okay.
Okay. Where theta is a weight that we have to learn.
Word, yeah, that you have to learn. That's it.
D is a degree matrix, and
That
A
is,
is adjacency
see,
matrix.
you can see the difference, right? It's a renormalized degree matrix.
Uh, oh, what is the meaning?
Adjacency matrix, you have zeros in your diagonals, right?
Uh, yes, a yeah, 0 in the diagonal.
So that leads to numerical instabilities while learning. What you do is add an identity matrix to the existing adjacency matrix. That will be your renormalized adjacency matrix.
And what is about degree? Renormalized degree.
How do you get the degree from adjacency matrix? How do you do that?
We just see.
You either sum over all the rows or sum over all the columns, right? To get the
Yeah.
degree.
Yes. Yes.
So from the renormalized adjacency matrix, calculate the degree for each node
Okay.
and make it into a diagonal matrix. That is the renormalized degree matrix.
Okay. We'll just take the renormalized adjacency matrix and then sum them. Okay.
Yes. Yeah.
Uh, and here, sir, F is a
Input feature. So you can understand how initially you saw an equation, right? H, A, and F, right?
yes, sir.
See, your F is here, your A is here. So that is what the filtering function is. You get it now?
Yes, sir. This was
Yeah, same thing.
okay.
So for each method, what changes is the H. H function changes.
Okay, so this is the final GCN filter.
Yeah.
Okay, so okay, so can you explain what it is written? So ith element is non-zero only when node
So if
ULB is
both the
existing.
nodes are not connected, it
Yes,
will be
sir.
zero. If it's connected, it will be non-zero. So what it essentially encodes is the connectivity information, right?
Yes.
If nodes are not connected, the element will be zero. If nodes are connected, the elements will be non-zero.
Okay, sir.
So what do I derive from this is you have connectivity information, you have neighborhood information. What do you mean by neighborhood? Let's say you and V are connected to each other. You can say that V is the neighbor of you, or vice versa. So that is what I mean by neighborhood. How do the nearby atoms influence my representation? That's it.
And this is called a spatial based filter.
Spatial based filter, yeah. So GCN can be viewed as spectral based or spatial based. It can be both.
Okay.
So this is the concept of spatial based filter. Again, there are different filters. You can go through them.
That's a multi-channel graph signal.
So right now, what you learned is each node will have only a single feature. Okay, single feature.
Yes.
But typically in deep learning, do you have just a single feature?
Like a single feature. So you
Let's
were
take
talking
house
of
price prediction. Let's see. Okay, house
No,
price
sir.
prediction.
No, different. Yeah, that's right. So many features. So many features.
Many features are there, right?
Yes. Yes.
Here, so same. Each node can have many features. Each node. So how do we combine it? That's it. How do I combine it? That's it. That is what multi-channel graph signal is.
Okay.
And again, you have to remember the final outcome. What is the final outcome?
So
Final outcome equation.
this is the final outcome.
No, no, no. Come down, come down. Yeah. See, that one is the final outcome.
So what is this symbol?
Here,
So filter
theta
parameter.
parameter. That's it. Weight. Think of it as a weight. That's it. You have to learn it.
Okay. Multi. Okay. Input and this is output. Okay. So so okay.
Yeah.
First GNN filter. So what is GNN filter?
Again, it's a different filter. That's it. Think of it like that. That's it.
And
So
what is LI, LJ,
those are labels for each node. Label. What do I mean by label?
label?
So you have
For node,
classification task, regression task. You have each for each input. You have a label, right? It's that label.
okay, output. You're
Yeah,
talking.
that's it. Yeah. So here you also use the output for learning representation. That's it. Think of it like that.
Okay. And here we have graphs change
Change.
filter. Yes,
I think if you go through the diagram, you'll understand what happens.
diagram. Okay.
So what do I do for generating Z feature? I take into account all my neighborhood features and do aggregation. You understand what I mean by aggregation, right?
So combine it.
Combining. Yeah, that's what happens. So this is spatial, right? I'm taking features from my neighborhood, aggregating it. That's it.
And where here it is written that we take random sampling.
Yeah, random sample. Yeah. So I don't take into account all my samples, some random sample. I won't take into U account U, V, Y, and W. Either UV or UY or WV, random sample. And again, how many samples you take, that is the hyperparameter.
Okay. And here we are passing it through activation functions. So why
Yeah,
it is
sigmoid
happening?
activation. Sigmoid
Yeah. So
activation.
why it is happening? So why we are passing?
Sigmoid activation, again, you don't want exploding gradients, right? If you keep on combining all the features, what happens if you use some large numbers?
Yeah.
Large numbers, that's always a problem, right?
Yes.
So you apply the sigmoid activation to keep the range between 0 and 1 so that your learning process goes on smoothly. That's it.
Okay. And we have aggregator, mean aggregator. So what
Yeah.
is meaning of the mean aggregator? We
You
are
just take
taking
the average. Taking average, that's it.
the average of
All the
what?
features, neighborhood features.
Here for you we have V, Y, and W. So we are taking average of
Yeah. Oh, yeah. U, V, W, Y. Yeah, everything.
so, so average of its feature matrix. No,
Feature vector. Yeah, feature vector.
feature. Okay.
You can do simple average or weighted average. That depends on. Yeah. LSTM, again, you learn the parameter and then do the aggregation. That's it. Theta
Yeah.
pool, that's the parameter. You can think of it as weight.
Okay. Okay, wait. Okay, sir. So just we
How?
have to remember these things, sir.
No. I mean, just remember the ideology behind it. That's it.
So we are taking maximum of whatever.
Some weighted
Yeah.
average. That's it. Think of it like weighted average. And the weights are determined by some learnable parameter. Theta, that's your learnable parameter. Do you learn it via back propagation, right?
Okay. Yes,
But in
sir.
the
Yes.
previous case, what were your weights? It was fixed, right?
Yes, sir.
Here you learn the weights. In mean aggregator, there are no weights. That's it.
Okay.
That's it.
So, but here we are taking max of just one thing. So
Hmm?
what it means?
What?
Here we are taking max of just one number. But there should be
No.
with
It's not one number. It's element wise maximum. See,
okay for all. Okay. Okay.
element wise. That's
And
why
here.
how do you learn it is start with an example. Okay. And you keep manually keep trying these steps. Then you'll understand what happens here. That's it.
So from where we get so example. So can we get a
So
example in
see,
book
you
deep
have
learning?
the equations. You have the equations. You know how to do coding, right?
Yes, sir. Yes, sir.
Just implement those equations in Python and see what's the output of each step. That's it. And
Also, can
actually,
we get
I also given the notebook to you, tutorial notebook.
also what we will get in the book deep learning on graph?
So more detailed information of why they do this. That's it. Why they do this step.
Uh, so will I will get example in that book?
No. Example, no. You won't. I think you won't get examples, but some intuition behind why you do this step.
Okay, sir. GAT filter.
Yeah. Again, it's a different filter.
We are taking activation function as a leaky ReLU.
Yeah.
Okay. And so what is happening here? Sir?
Mhm.
Stabilizing learning process. We are. This is the symbol of
Different
con.
concatenate. Yeah. Different attention hits. You might have learned about attention and deep learning, right?
Attention.
Hmm.
So I don't remember it. So, so
Yeah.
can you explain the size? What is happening? So we are taking summation, but what this
Again,
mean?
see the parameter theta is there.
Yeah, we have to learn theta.
So again, it's weighted average of the features from neighborhood. Okay.
Okay.
And you are learning those weights.
Okay.
That's the basic idea behind all these spatial based filters. That's it.
Okay. And we have age feature. So
Edge features.
learn
Similar to node features, there are edge features.
okay, and here we have a message passing neural.
Passing neural network.
So, so what is happening here? What it means? We are
So
message function. What?
message is aggregation. You are getting
So,
features from neighborhood.
so
Okay.
what is message here?
Message. You are collecting information from your neighbors. Think of it as you are collecting information from your friends. That's it. Okay. See, let's say you go to a new locality. Okay. You don't know how it is, but again, you have some nearby neighbors that have information on this locality, how it is, what to do, and everything. You're basically gathering information from everyone, right? You're getting
Yes.
messages from everyone. That is the message function. And how would you process this information? How would you use this information? That's what is update function. That's it.
Okay. Update function.
How do you use this message? That's the update function. That's it.
Okay. Okay, so I have seen lecture until here, so I will
Okay, okay,
see the whole lecture and I will ask it
okay,
out tomorrow. So
okay.
there will be a live class tomorrow.
Yeah, it's there. Deepesh, timings?
Yeah, so I think yeah, timings would be 7:30, I think. So I will
Okay.
ask, so is 7:30 suitable for everyone? No one is,
Yeah.
so
So
Aditya
one is
responded, 7. So Aditya, for you, what time is suitable?
7:30 is
Yeah,
good.
7. So it would be around 7:30 only, like today.
Okay, sir.
Aditya, I see that there is one more question you asked on the chat regarding this question. What is the average degree of tumor overlap graph constructed from ATGACT? Is this question
Yes,
answered to you?
yes, sir. This question answer.
So you know that. So correct answer is, so there is no confusion in this question left now, right?
No, sir. No, sir. No confusion.
And Roshan Rajiva, so is the question correct as well as the options for this question?
Sorry, can you come again for which question?
Let me share my screen. Let me just quickly share my screen. This question,
This question
Rajiva,
is
this
correct.
question.
This question is correct.
This question is correct. So only one question out of all the questions that needs some change. Otherwise, all the questions and options and the correct options is also given. Correct, Rajiva? If
Yeah.
you can confirm that. So,
Yes, yes.
Cool. Uh, thanks. Thanks. That was the only thing from my end. So tomorrow we will have another live session in which primarily Karthik sir's questions you can ask Aditya and for everyone who will be listening to this recording. Okay.
Okay, thank you, sir.
Yeah, thank
Okay.
you.
And if there is anything like that we have a group chat, so you can mention it there. All right. Any questions
Yes.
or any queries that whatever you have. So all the best. Happy learning.
Okay, thank you, sir. Thank you, sir.
Thanks, guys.
Yeah, thank
Bye.
you. Thank you.
Thank
Bye.
you.